So today's the 27th, which means we're supposed to be finishing chapter 2 today. We'll get as far as we can. I think we'll probably finish it, even though we're getting a teeny bit of a late start. And then next week is chapter 3. Some people start to really feel that linear programming gets a little harder when we get to chapter 3 because chapter 3 is analyzing the output. And I'm going to show you how you can quickly make decisions by looking at that output if you do some calculating. In my experience, and this is true in real life, in business, that things change all the time and you have unexpected things take place. So when you're doing something, you say, oh, here's the optimal solution, and you have next week all planned, or next month, whatever you just found the solution for, whatever decision you're making, all of a sudden someone at a meeting will go, whoa, something just changed. You got to make a decision fast. What I'm going to show you is when you analyze this output, you can quickly do a little math and make that decision without having to do the whole thing over again. These problems we're going over are so small, you're going to say, I'll just do the whole thing over again. But in real life, they're not this small, and doing it all over again is probably more work than the little bit of work of analyzing the output that we do a little math to. Don't worry. I'll break it down for you. We'll record it. You'll forget it. Hopefully you'll watch it. All right. So, let's call this a slight review. And what we're going to do is Casey gave me a great example problem to use. I was just going to and then we're going to, what you today, I need you to understand. I know I mentioned a couple of these in Tuesday's lecture, but I need you to understand all these today like you know exactly. Because in your homework assignment that's due on Tuesday, you've got to do all this. Every one of these are part of that assignment. So I'm going to show you, I'm going to do all of this with this example one that he's been working on it to try to make sure he gets this. 2a plus 3b. Now, is this in your book? If people didn't want to have to write all this down, is this in the back?
Chapter, yeah, it's
chapter 2,
question 10.
Number 10?
Yeah.
And the answer's in the back?
Yep.
Okay. So somebody can even check my answer. Let's see where we go. Who knows? Hey, all of you make mistakes, period.
That is true.
If there's a human involved, there's probably going to be a mistake eventually.
And then does the AB greater than 0 matter at the end? Because there's a third one.
Yeah, it says it's equal.
Oh, no. Okay. Show them. I got to show them what you're talking about. I want everybody to see that. What he's saying is, on this problem, it looks like there's another constraint. But really it's not. But really it's not a constraint. Hang on. What do I got to do? Auto. Good? We going?
It's just to make sure that the values are above 0.
There we go. Okay. For the whole semester, and I thought I mentioned this.
You did. I remember now.
Every single variable, decision variable, in every one of these linear programming problems will always be either 0 or a positive number. That you do not need to include this in any of your answers, any of your assignments. That this is assumed. Notice S and D are the two variables here, and these are what have to be decided on for this example problem. And this right here says S and D are greater than or equal to 0. You'll see this at the bottom of all of chapter 2. It's just saying these variables are going to be positive numbers or 0. They're never going to be negative. We're never going to say only make 10 bikes and negative 3 cars. You just can't do it, so they'll never be negative. For this whole semester, this whole class, we're assuming the variables are going to be either 0 or positive. You don't have to include that, you can just ignore it. And on the software in Excel, you don't have to enter them. It also already assumes that the variables are going to be positive or 0. So, here's our problem, right here. If I said to you, solve this linear programming problem using the graphing method and show all your work in detail. This is what we're going to do. I'm going to show you all the way from beginning to end. You ready? The first thing I would do is I'd say, okay, I need to graph these equations. That's the first thing. And I can see we got numbers like 5, 3, 2, 2 divided, 6 divided by 2 is 3, 6 divided by 1 is 6, 15 divided by 5 is 3, 15 divided by 3. So what I just did allowed me to see what approximately how big my graph needs to be, how big the number should be. Because I've done so many of these, I know that we're going to have a situation where we take 6 divided by 2. And now we're going to have a situation with 15 divided by 3. So I'm going to go ahead and put my graph right here. This is probably, I got to leave enough room in case, you know, I showed you Tuesday that sometimes you have to go into the negative lines, but you'll always extend into this positive quadrant right here because your optimal solution is in here, not here. So I'm going to extend this so you see these axes. In a real graph, you have all these other 3 sections here, but all we're focused on here. Even if you have a point, like on Tuesday, way down here, and then connected to a point here, we extended it up into this section so that we knew that it would be part of the solution. All right, I'll just leave that up there. Let's just keep going. 1a plus 2b, I make it equal to, I'm not even putting the 1 there, plus 2b equals 6. I'm going to graph it. I want to make sure everybody can see what I'm doing. Can you guys see this? I'm just going to make it real small right here. Put a 0 comma something, and then something comma 0. I know this tells me I'm going to put a 0 in for, I'm going to put the variable a right here, the variable b right there. I'm going to figure out where b would be if a were 0. I'm going to figure out if b were 0, what would a be for that, and then that will tell me where it crosses the axis. And then I'll graph it. By the way, this axis is our b, and this is our a. The first number is always your horizontal axis. The second number is always your vertical axis. So I put a 0 in for a, which means I can just cover it up. And it says positive 2b equals 6. Divide both sides by 2. And I get b equals 3. So I know when a is 0, b is 3. A is 0, b is 3. And I know this is going up to, it could be 5, 6, 7, 8. So I'm going to go 1, 2, 3. Whatever spacing I have here, I need the spacing to be darn close as you can on the horizontal axis too. Wait, what's this? Okay, so 0, 3. There's that dot. Now I'm putting a 0 in for b. I'm covering that up. I get a equals 6. There's no math to be done. It's 6. When b's out of there, it says a equals 6. Right? Because there's only one a. Nothing to divide. So 6, 0, 1, 2, 3, 4, 5, 6 is right there. I should have made this bigger. I could tell already. You ready? I need a straight edge. Yeah. Hang on. How's that? I'm awfully proud of it. Next. The next one is 5a plus 3b. I make it equals 15. Oh, I should have shaded. My fault. Which way did the shading go? Obviously, it's going to go down. But to make sure, I'll pick my favorite point on one side of the line, 1, 1. 1 times 1 is 1. 1 times 2 is 2. 2 plus 1 is 3. 3 is less than equal to 6, so the shading's for sure going this way. Now, I don't have a way of, I guess I could, of doing it lightly. I'm going to end up erasing some because I'm sure part of this isn't going to overlap with the other constraint, possibly. Now, here's the other constraint. I'm doing the parentheses like this, putting the 0, comma, something, comma, 0. Same exact way. Putting a 0 in for a. I'm covering up a because it's gone. You put a 0 in. I get positive 3b equals 15. I divide both sides by 3. I get 0, 5. I'm putting it down at 0, 5. I put a 0 in for b, cover that up. I get 5a equals 15. I divide both sides by 5. I get 3. So that's right here. And now I'm going to connect these. Hang on. All right. This is less than equal. It's obviously the shade's probably going to the left because of the particular angle it has, but I'm going to pick 1, 1 again. My favorite point on that side of this line that we just made. Plug it in. 1 times 5 is 5. 1 times 3 is 3. 5 plus 3 is 8. 8 is less than equal to 15. It's definitely going to be going this way. Now, I'm not going to do this area right here because I can already tell it's not going to overlap with the other one. And so I need to erase this area right here because it's not going to overlap. The area that's overlapping is right here. Right here. Okay? And now I would get this eraser, get this out of here. And to really make sure and emphasize, I darken up the edges of the, what am I just darkened up the edges of, what is that called?
Feasible region.
Feasible region. And I'm going to identify it. This is the feasible region. I'm just putting a little arrow there. I'm going to show my extreme points by putting nice big dots on them. Look at that. How many extreme points? Extreme points right here. Extreme points equal how many? Four. I'm only doing that because I know your homework says, how many extreme points did you find? Just pretend like I'm doing the homework. But it's not these extreme points. So you know. All right? The homework's posted on it. Anybody see it? Yes. Did you already start it?
I didn't see it.
No. So feasible region, extreme points. What's next? We take the objective function. We figure out where the objective function would land and what angle it would be at. And then we realize it's a max problem. So knowing it's a max problem with these extreme points, 0, 0, we know what that point is. That's 3, 0. This point is 0, 3. We know 3 of the points. The only one we don't know is there. Matter of fact, this is one of those rare occasions where you can literally plug in every extreme point by calculating that one. Whichever one, when you plug in what A is and what B is, whichever one gives you the biggest outcome for this objective function would be the optimal solution. Now, in reality, there's no way you can do every one of the extreme points because you're going to have much bigger problems with many more extreme points. And they're not all right on the line like that, so it's not so obvious. But in this case, I could enter in 3, 0, and I would get 6. I could enter in 0, 3, I get 9. Out of these two, there's the better one. That is not our optimal solution. And now I could enter 0, 0, and we know that's not our optimal solution. We got it down to 2 points just by taking these extreme points that we already know the numbers for. Odds are that's going to be our optimal solution compared to this, which is 0, 5. Because 0 times 2 is 0, 5 times 3 is 15. That's the biggest out of these three. But this one's using both numbers and not one being 0, so I would imagine that's going to be bigger. Let's do this as if we don't know that this is a bigger problem. And we're going to take this objective function, 2a plus 3b. Are you ready? This is the part where everybody goes, I can't remember what to do from here. You're going to pick an arbitrary number, any number you want, and it can be a different number than anyone else would pick. They make it easier for yourself, though, is you're going to want to pick a number that both 2 and 3 go into evenly. I find it to be much easier that way. I know in the PowerPoint, though, that this is where we're at right now, right here, if you can see it. In the PowerPoint, we put that first line there because we picked an arbitrary number. That made sense, and it was, and both 5 and 7 went into even, 35. But when we wanted to see, exactly which extreme point was our optimal solution, instead of using a straight edge, the PowerPoint recalculates with bigger numbers. Now let's use 39. Oh, look now. Now let's use 42. Oh, look now. And as you can see, these lines are all parallel to each other. Once you do one of these, they're all going to be parallel to each other, no matter what number you use. And it's just a matter of, we now have done so many lines that you can see that there's no way that's the optimal solution. And that's really down to these two. But these two are so almost evenly apart from this line that you've got to go a little farther to see which one it would really be the very last spot that would touch. What if your line's out here? What if you use too big of a number? It's still right with that one. You would just take a straight edge and go back and see where the very first spot it touched instead of maybe. Get it? So you just kind of, all right. And as you can see, that would be it. In our case, what number do you want to make 2a plus 3b equal to? 6. I got a lot of 6s. Here we go. Arbitrary number. Same exact thing. put a, I'm going over here, put a 0, comma something, and put something, comma 0. I'm putting a 0 in for A, 3B equals 6, I divide both sides by 3, 2. I put a 0 in for B, 2A equals 6, divide both sides by 2, 3. 0, 2 is right there, and 3, 0 is right there. Hang on a minute. And now I like to kind of, like the PowerPoint, I make this line like really thick. That. It's real obvious that's the objective. I got my angle. I'm going to take a straight edge. And if I pass that point before I pass that point, then I know that's our optimal solution. But if I pass that point before that one, then that's our optimal solution. You tell me, I got to stay parallel to this. Well, I better go this way. Okay, you tell me, ready? Out of those 2 points, you ready? Am I parallel? Stay parallel, stay parallel. Look at that. I'm passing one of the 2 right now at the top. See it? You guys see it over there? Okay, keep going. There's the last, am I still parallel? There's the last spot it would touch. And how did I know to go that way? Because I went in, I could go, I just, don't have it. I could pick a point on this side and pick a point on this side, and whichever one makes that bigger, that's the direction I want to go because this is max. If it were min, I would know to go this way. Again, I could pick a point on either side. Whichever one makes it smaller is the direction you want to go. So we now know our optimal solution. Got to identify your optimal solution. So we go optimal solution. And I'm going to point at that extreme point right there. What constraints, what lines, what equations are forming that point? Less than equal to what? There's only 2 constraints, you guys. Can anybody leave the room? Less than equal to 6 and less than equal to 15 are the 2 lines forming that point.
This is less than equal to 6.
Is that 6?
Yeah.
What did I say? Less than equal to 6. Isn't that the 2 lines?
Yeah.
And less than equal to 15 are the 2 lines forming that point, right? Because those are the lines forming that point. Those are the constraints. You've just identified the binding constraints. Let me make sure you understand. The binding constraints are any constraints that are part of that optimal solution. That when you, it's the line that's making up that extreme point. Yes?
So another way of saying that could be like where the 2 lines are intersecting.
Well, you're going to have 3 lines, 4 lines, 5 lines. It's where the 2 lines are intersecting at an extreme point. That's the optimal solution.
Oh.
It's got to be the lines forming the optimal solution. What if the optimal solution were right here? There's only one line that is binding. The one that's crossing the axis here. I'm sorry, that's not even on a feasible region. I'm not here. Then it's only that one is the binding constraint. So whether it's 1, 2, there could be 3 lines at that point. Whatever lines are forming the point that the optimal solution's at are your binding constraints. In your homework, it says, identify the binding constraints. And I would go, here we go, binding. I mean, you can do this any way you want, but there we go, there we go. I just identified that these 2 are the binding constraints. Now, don't get me wrong. Next week, we're heading to where you're going to have, for sure, more than 2 constraints. But, I mean, it was the only 2 constraints we had. Usually, there's more than 2 constraints, and the other ones are not binding. They're important, but they're not binding. You ready? The reason I'm mentioning all this, we haven't even gotten to the optimal solution yet, is because we are going to be getting to where slack or surplus. Slack or surplus is calculated by when we find this optimal solution, we're going to plug it in for A and B in every one of these. The objective function, we plug it in to get that objective function value. Why is that I forget to put the objective function value on here? I know we talked about it on Tuesday, but that's a big part that you've got to make sure. The objective function values, when you take the optimal solution and plug it in for the variables, and what that it calculates out to. It's going to be the max of whatever this represents that you can get to. Staying within all these limitations. So that's the objective function value, the max or the min outcome when the optimal solution's in there. You ready? We're gonna figure out the optimal solution, plug it in there. My next sentence was gonna be, we plug it in this constraint, and if the left-hand side doesn't equal the right-hand side, you've just found either slack or surplus. We'll plug in the optimal solution for A and B in this constraint. And if the left side doesn't equal the right side, you found either slack or surplus. In your homework and on the quiz, you will have to tell me what the slack or surplus amount is, and whether it's slack or surplus. And I want to emphasize something. This happens every semester. Somebody will say, oh, when I put in the optimal solution, because it's a binding constraint, the left side ended up equaling the right side. So it was 0. Even if it's 0, I need you to tell me that it's 0, slack, or surplus. You need to show me you can recognize whether it's slack or surplus. And here's how you recognize it. If the original constraint you're evaluating is a less than equal, no matter what, that's slack. Period. I don't care if the number's bigger, smaller, whatever it is, that's slack.
Can you repeat that?
You ready? You have to calculate how much slack or surplus exists for every constraint. And when you put in the optimal solution for the variables for a constraint, the difference between the left and right, even if it's 0, the difference is slack or surplus. You want to identify it as slack if the original constraint is less than equal. Period. No, there should be no debate on it. It should be clear. It doesn't matter, oh, what about if this is on the other side, or da, da, da. If the original constraint says less than equal, whatever you just calculated is slack. The word slack.
So we're putting the optimal solution
In for here, here,
Okay.
and you're going to see if there's a difference here, and you're figuring out what this calculates out to, because that's the max or min that you can get to. So once you get that optimal solution, you got to plug it in everything now. You'll see on the output it gives you, here's the slack or surplus for this one, here's the slack or surplus, here's the objective function value. It plugs in the optimal solution for every constraint and the objective function. You calculate that number. And even if the difference here is 0, you're going to put 0 slack or surplus on this one, if it were 0.
Slack.
That's right, because it's less than equal. If this is greater than equal originally, then it's surplus. I'm serious, that's the easiest way to remember whether it's slack or surplus. Just look at the constraint you're evaluating. If it's less than equal, slack, greater than equal, surplus. It's just such an easy point, you guys. I mean, just to write that word slack or surplus is like a half a point that's being given to you, because there should be, the hardest thing for students, it seems like, is to remember to add the word slack or surplus. I get it left off all the time. So make sure, okay? On this quiz, for sure, the second quiz. By the way, once you get past this graphing on the second quiz, you're never going to see it again. Okay, we just got to get through this. This is all about getting you the fundamental basis of how all of this developed and how it originally comes about. Everything you're going to see from this point on in Excel and software is being done automatically, just like this stuff. This is what's happening on that software. Just within seconds, that's the difference. Okay? And where we had to do it manually in my day, which was crazy. When we used computers, we had to use what are called programming index cards. And you'd have to take these cards, your program would be made into these cards that I had to carry around in bags, just so heavy, so big, bigger than this whole bag. And then you go to the computer room and you take these cards out and you set them in the reader. This is how computers were in my day. And it goes and reads your program. You're not just typing it and saying, hey, read my program. You're making these cards, putting them in, and it reads your program. Can you imagine?
Those are the ones with that punched out holes, right?
Push out holes. That's the only way to run a program, even in basic language back then. You guys. Just trying to tell you how much. And you can fly. All right, that's too much. All right. There we go. We're going to find out the optimal solution. What do you guys want to do? Substitution method, addition method, subtraction method.
Substitution.
Let's do it. And when I look for substitution method, I look for a variable that doesn't have a number bigger than 1, because it's so much easier to isolate a variable that's by itself with only a 1 and no number means 1. So I'm just going to subtract 2b on both sides on this first one. So I go a plus 2b equals 6. Now I'm minus 2b on both sides. So what you have left is a equals 6 minus 2b. I isolated a, I go to the opposite equation, and I will put in for a 6 minus 2b, for the A. Now A will be gone, and I can use algebra to figure out what B is. So this will now be, I'm taking this whole thing right here and putting it in for A in the other one. 5 times 6 minus 2B. And now the rest of it is plus 3B. I'm going to make it equals 15. I just want to get that optimal solution, so I'm just making an equal sign. You got to do multiplication first before you add these like terms together. So 5 times 6 is 30. 5 times negative 2 is negative 10b plus 3b equals 15. I'm going to combine like terms. Whoops. That's supposed to be a b. I'm going to combine like terms, and I'm going to subtract 30 from both sides at the same time. So I'm subtracting 30 on both sides, and I'm putting together like terms. Negative 10b plus positive 3b leaves me with negative 7b, right? And on the right side, 15 minus 30 is negative 15. Now I divide both sides by negative 7 to get this b all by itself, positive b. What's 15? That'd be 2.11? 2.4? 1.4. 2.14. B equals 2.14. Positive 2.14 because they're both being divided by negative 7. Everybody with me? Did I go too fast? We're okay?
A little too fast.
Darn. What I did is I took the first equation and we decided we're going to use the substitution method. So I have to isolate that A by itself so that I figure out what A equals so I can substitute it for A in the other equation. So for me to get A all by itself, I had to subtract the 2B on both sides. That got me here. A equals the 6 minus 2B. Now I took that and put it in for A in the other equation. So 5 times 6 minus 2B, and then the rest of the equation plus 3B equals 15. Now 5 times 6. Here's the mistake some students will make is they'll put like terms together before they multiply. You've got to do this multiplication first and then put like terms together. That got us to the 2.4. Now, I can take that 2.4, put it in for B, either equation. Doesn't matter, I'll get the same answer, but that will be where what A is, and that will tell me where they're crossing. So I'm going to use, let's use this one, I guess, it was easier. Put 2.4 in for B, so I get, run out of space. Is any of this on, do I have any other space I can use? How about here?
Yeah, we got the right.
Huh?
Just put all that right.
Yeah, but is the camera going to see that?
Yeah.
Okay. Where was I? I put in 2.4 in the first equation, is that what I said?
Yes.
Okay, so A plus 2 times 2.14, am I correct so far?
Yes.
Equals 6? Equals 6. So then 2 times 2.14 is 4.28. Help me out. 4.28? 4.28, this is plus A still, equals 6. Subtract 4.28 on both sides. A equals 1.72. Anybody confirm that?
Yeah.
Is it really?
Yes.
Good. I shouldn't be so surprised. So A equals, I already forgot, 1.72?
Yeah.
1.72. 1.72, that's a 1. And B equals 2.14. You know what I love about this is that they're, even if you thought that was 2.2, this proves that you need to always calculate it. Because there's no, I could have guessed that that may have been like 2.2. There's no way it is. 1.17 and 2.14. Okay. So far, extreme points, feasible region, finding constraints. Now we got to do the objective function values, slack, and surplus. We're almost done. Ready? I got to put in 1.72 for A up here and 2.14 for B and calculate this out. So I'm going to put objective function value. Objective function. That's OFV, even though I made a mistake there. Ready? 2 times 1.72 calculators plus 3 times 2.14 more calculators. Darn. Wait a minute. Yeah. Hey Siri, what's 2 times 1.72? Thank you. Siri. Hey Siri. Come on. What is 3 times 2.14? Okay, 6.42 plus 3.44. Well, I think I could be faster than this series. This is too, that's too long. I'm gonna have to bring in Alexa. Siri will be disappointed. You'll be laid off. How do you support little series? Are you ready? Okay, I got 9.86. Does that sound right?
Yes.
The most we can get this up to, and stay within these limitations, is 9.86, whatever that represents. Dollars, profit, time, hours, whatever we're trying to max. 9.86. We just found the objective function value. That's an OFV that you have to calculate in the future. So realize that. Now slack and surplus is all about taking that optimal solution, 1.72 and 2.14, plug it into each constraint to see if there's slack or surplus, if the left side equals the right side. Now, as long as we did, was any rounding involved in these, or are these exactly 1.72 or 2.14? They are exact?
There's rounding.
Okay.
Yeah, because it would be.
If we
9.85.
didn't round this, and we plugged it into each of these constraints, here's a little hint to save you a ton of time. And I'll allow this as your work. You ready? When you know that a constraint is a binding constraint, then you should know it will never have any slack or surplus. It will always be 0. And I'll accept you writing, because this is a binding constraint, the slack is 0. Why did I just state the word slack? Because it's a less than equals. And that would be, you don't have to show me the work that they're equal each side, especially when rounding, you're going to be off a little. They won't be exactly equal. But if you know a binding constraint is always 0 slack or surplus. And usually you have many constraints, and only the constraints that are binding have that 0 slack or surplus. So if you remember that, I'm allowing you to say, I'm not going to plug in 1.72 and 2.14 and do the calculation because it's a binding constraint. You can write, because it's a binding constraint, showing me you recognize that this is the reason you're about to write. I know it has 0 slack. You're still showing me that you identified if it had any, it would be slack. Huh? Go ahead.
And that would be the same for surplus as well.
Dang, she jumped right into my answer my question before I could ask it. I was going to say, now on the second constraint, how would you calculate the slack or surplus? See? Because it's also a binding constraint, and that's what you just said?
Yeah.
Okay.
No, I'm writing like if it's surplus or if it's surplus and not slack.
Oh, yeah, same thing. If it's a binding constraint, you would use the word, because this is a binding constraint, I know that it has 0 surplus because it's a greater than equal. Everybody hear that? So really, you only need to really plug these in to any constraints that are not binding. The constraints that are not forming the optimal solution. Then you plug in the 1.72, 2.4. It will be different than the other side. If it's not binding, it will have either slack or surplus. Every problem does. And so you find the difference, and then you write the difference, show a little word, or at least set it up, and then write the word either slack or surplus. And if this was a non-binding constraint, you would write the word slack, right? Got it? How do we feel? Can we all do this? How are we doing on time? We gotta go to the software now, is that what's next? Did we cover it all? You know binding constraints, you know slack or surplus, feasible region, extreme points, objective function value, I think we covered it. Just kind of show you what it says in here. Here's your slack and surplus. I want to see if it says. Okay, slack variables are the constraints that are less than equal. Surplus are greater than equal. So there's that to kind of help you remember that while you're taking the quiz. Here's the corners of vertices of the feasible region are referred to as the extreme points. I described it as any place there's 2 lines crossing touching the feasible region, that's an extreme point. Even if one of the lines is the axis. So both axes are crossing right here, but they're touching, that's an extreme point. One axis is one equation constraint line, that's an extreme point. So anywhere there's 2 lines crossing touching that feasible region. Anyway, so it's all in here. We've finished this. We're going to the output now. Is that what this is, computer? You ready? Let's do the same problem. You get on lab anywhere. Somehow you got it to work. And then somehow you went down and you found the program with the word "the" management scientist. I'm told don't click on the one that says Windows 10, click on the other one. and it will open up a lab computer that's not Windows 10, which will have the management scientist software on it. Or bring a flash drive, or borrow this found flash drive that hopefully the owner will come back to do. They got Are you recording this? Excuse me. Wow. All right. You click on it. If you try to use this on your own computer, you might get an error statement. It's very common, especially newer computers. Instead, if that happens, go back to it. You got to find it and do this. Has anybody? A couple of you got this. Did you guys try this on your home computer? Anybody who got this? Did you try it?
Yeah, it works.
Did you get the error message to start with?
Yep.
Okay, when you get the error message, go back. This is like, let's say you open up the folder. This is what you're going to see. You can run it from your pen drive. You don't have to put it on your hard drive. Or you can open up the folder. You don't have to install it. I actually never install it. I always just run it from right here, the folder itself, instead. And so, if instead of double-clicking on that to run it, if you right-click, everybody see this? When you get the error message, right-click here, then left-click, see where it says Run as Administrator? Left-click there, and then it asks you for this permission, and then it'll run. And it looks like that. Now, if I close this, because I ran as administrator, every time you double-click it, it'll work now. You only have to do that the first time. So the first time, if I get the error message, it will remind you, email me if you can't remember. You right-click on it, run as administrator. Okay, which module are we going to use here?
Linear programming.
Number 1, linear programming, very good. It's going to ask you, how many decision variables are in our problem up there? 2, that's right. They are A and B. How many constraints are in this particular problem? 2. Only 2. Very rare, and so few. Is it a max or a min?
Max.
Very good. Now, I like to change the variables. It always comes up x1, x2, x3, however many variables. I like to change them to whatever variables we're using. So I'm going to switch them to A and B. That just makes it more visual to me. There's the A, there's the B, and notice it changes automatically below for the constraints once you do the one at the top. Now, it wants you to put in whatever number is with the A in the objective function. We're doing the objective function at top. Look at A in the objective function. What number's with it? 2. What number's with the B? 3. Let's go down to the first constraint. What number's with the A? 1. What number's with the B? 2. What if there's no number with the variable? What number would you put?
0.
Just make sure. 1.
Oh,
1. 1. If there's no, you know where it had A is less than or equal to 6 and there's no B? Put a 0 in there. If there's no, or leave it blank. The software assumes blanks are 0. I always throw a 0 in them. That's what I do, just to, so I visually. Now here, you do not enter less than equal. It assumes the equals there. You just put the less than or the greater than, unless it's an equal, then you put an equal. So I'm just putting the less than. It knows it's less than equal. And the right-hand side is a 6. Okay? Second constraint, what number's with A?
5.
What number's with B?
3.
And what's the right-hand side? 11?
15.
Oh, whoops. 15, and is it less than? Less than. There we go. Boy, this was too easy. I'm going to hit solution. Now I'm going to click on solve. I'm going to show you where the answer's at. What did we find the answer, just so we can compare? 1.72 and 2.14? This probably won't round. It's 1.714, so this was rounded. Boy, incorrectly rounded. And 2.143, very good rounding. But we should have went one more digit. Is your optimal solution. You see where I found it. The optimal solution is always near the top, and you just look for the variables, and then you look at what values those variables are. There's your optimal solution. Notice at the very top, the objective function value. What did we get? We got 9.86, but we rounded. Oh. 9.857 or 9.86, same thing, right? Everybody see at the top? So that's where you would find your objective function value. And when you're doing your homework, you want to use this to make sure you've got the right optimal solution, that you use the right objective function. If you're taking a quiz, And you do all this because you have to do it manually, and you want to make sure you have this right, this right, this right. Well, open your laptop. The software, you're going to need the software on the laptop. And maybe we could get the laptop cart if someone reminds me, because I think the software is on every one of those laptops. Anybody know what I'm talking about? Have you seen the cart? I don't think there's enough. How many? Yeah, I think we have 32 in this class. I think there's like 30 on there. So I think we have enough to cover everybody. If you wanted the software during the quiz, let me know and I'll reserve it. And are you ready? Does anybody see where the slack and surplus would be identified?
Mhm.
You do? How much slack or surplus does constraint 1 have according to the software? 0. It will never tell you whether it's slack or surplus though. That's the only bad part about the software. You still got to look back at the original constraint to determine whether it's slack or surplus. And in this case, it would be what?
Slack.
Exactly. Constraint 2, how much slack or surplus?
0.
And is it slack or surplus? Even though it doesn't say. Next week, you're going to learn about this. This is where people start to go, oh, why is this getting hard? Right here a little bit. I don't want to scare you too much. And then here, right here, it says, hey, right now, whoops, hang on a minute, I got to think about this. Right now in the objective function, you've got a 2 with the letter A. If for some reason someone comes into your office and says, hey, no, that's not going to be 2. Well, let's say that's profit. We're not going to make $2 on each one. We're only going to make $1.50. Oh my God, do I need to redo this whole problem? Look at 2. As long as that 2 in the objective function stays between $1.50 and 5, nothing needs to be changed. Everything's still valid. I mean, the objective function value will have a slight change, but the optimal solution, if this is a production problem, you don't need to call out to the floor and say, whoa, stop production, we're making the wrong quantity because this changed. If this stays in the range, the optimal solution, 1.714 and 2.143 are still optimal. If someone walks in your office and says, oh, no, we're not making $3 off each one of these, we're making $5 off each one. Is my optimal solution changed? Do I need to redo this? Because why? That's right. And the 3 can only go as high as 4, or as low as 1.2, and the optimal solution stays the same. But if something happens and this falls outside of that range, everything's going to change. And you need to recalculate. So, now, down here, this is the right-hand side of each of the constraints. You'll have each constraint in the right-hand side. Also an upper and lower limit. Let's say this represents 6,000 pounds of raw material. You aren't going to believe this. We were in the warehouse. We just found an extra 1,000 pounds. We'll take the 6 to a 7. How do I say this? We haven't even learned dual prices, but the question is going to be, is the dual prices still valid? Are they still accurate, or do we need to redo this whole thing if the 6 goes up to 7? No, because it could go all the way as high as what? 10, that's right. You're now, don't get too comfortable with this output. Every software has different formats for the output, but they're telling you all the same information different ways. You'll see all these same numbers if you used a different software, but the way it's all being communicated to you is different. Even your book. Here we go. Okay? I'm on page 111 in case you have a book, if you want to follow up. But right here, 111, look at constraint 1. What's the current value? Remember the current value was 6 on this one? And go back to this. All right, ready? What's the current value of constraint 1 by looking at the output here? Even though you know what it is, but where do you see it? Constraint 1. You see the current value? Right here? Right? But look at this. Where's the current value? Whoops. Where's constraint 1's current value here? You see where it's in a different spot? It's over here, not in the middle. And if someone's, I've had this happen all the time, if you're working on a problem fast, you think that's your right hand, and this is your lower and upper limit. This isn't even giving you upper and lower limits. This gives you, this one's showing you the information and giving you the allowable increase, the allowable decrease. You would have to add 52.36 to that to find the upper limit. And you'd have to subtract 91.6 to find the lower limit. It's the same information, just being communicated to you in different ways. And actually, when we get more into this, you'll realize that you would use the amount of the increase instead of the upper limit, and the amount of the decrease instead of the lower limit on several of the questions that will be coming. So there's advantages for some softwares compared to others, and they all look different, but they're actually giving you all the same information. Let's see. Look at this on the objective function. This one has 3 variables. And if you notice, the current numbers are here instead of in the middle. Same thing. So this 10 could go all the way up to 12.51, or it could go all the way down to nothing. You can't go down. And as long as it stays between 12.51 and 10, the optimal solution is still valid. It's the same information, but you have to read it kind of differently than the one that's in this PowerPoint, for example. And the one that's on the software that we're using. All right. Real quick, another question is, in the constraint number 2, we just found out that somehow or another we lost 3,000 pounds of this raw material, 3, so we're down to 12. Is the dual prices still valid? You don't know what the dual prices mean yet, but that's the question you ask yourself when you're evaluating the constraints right-hand side. Is the dual price still valid? Yes or no? I can see a lot of shaking heads, yes?
Yeah.
Because why? I said 15 is going down to what?
12.
12. And you look down here and you said the laws is between 9 and 30. But if you were looking at the book, it would have been, this could be the right-hand side, this could be the amount it could increase, and how much I was decreasing by 7. If this is the amount it could decrease, you're just comparing the 3, what did I say, decrease by 7 or decrease by 3? To 12, I said, right?
Mm-hmm.
I'm decreasing it 3 units. You just go, okay, this can decrease 30 units if you're looking at the book instead of this. So what I'm trying to get at is, make sure to read these titles up at the top here and realize how to interpret this, because it's different here, it's different on another software that sometimes we use for this class. We're not going to use this semester. And it's different on Excel. Excel doesn't put it in this exact order either. But it gives you the same information. Same information, just different ways. All right. Can you do the software? I would practice one maybe. When you do your homework problem, maybe. And you know what? Maybe I should add that to the homework problem, is that you have to then, once you solve it manually, you go into the software and print out your results. But then everybody just photocopy everything.
And we can find this on Blackboard, right? The program?
No.
It was somewhere.
I can't get it on Blackboard, but you can use, what's it called? Lab Anywhere?
You can put it on the shared drive. Put it on the shared drive.
How do you, what shared drive is that?
Is it? Okay.
Is there a shared drive on Blackboard?
No, you can just figure out with Google Drive or whatever. Put it into a shared
I don't think I've ever set it up.
Okay.
I've never used it.
Okay.
I have a shared drive with school management that we put stuff, but that's secured and nobody can get to it.
Right, but you can make your own.
It's not Google, so it's, I mean, it's a shared drive that when I go to the internet, all of a sudden I got this folder.
They just add a link to Blackboard.
Really? All right, I'll have to go to Google read that in my spare time. You ready? So where are we at here? We're going to do Excel one more time, but we're doing this other problem. Then we have an in-class assignment. What time is this class over with? 6:45? And we have an in-class, so we got 11 minutes. You ready? Let's say I just opened this up off of Blackboard, and everybody should download this because you're going to find this so useful. I have it set up for you for 5 different variables. Right now, we're only going to use these 2 variables, but you know, look at how many different times you can use this through this class, because we're getting to where you're going to have even more than 5. And we're getting to where you're going to have more than 3 constraints. You just got to keep shifting this down, okay? So we'll do this one right here. The constraint 1 has a 1 and a 2. Let me switch this for now to an A, and this is a B. And this is 1, and that's 2. The next constraint is 5 and 3. 5 and 3. Just lucky. I'm getting rid of this whole, look at this, delete, row. That constraint's gone. The numbers with the objective function are 2 and 3, right? Now I'm only going fast because I've already demoed this last week, or 2 days ago, so this is all review. Right-hand side of constraint 1 has just a coincidence, a 6, and this is 15. All right, so I have all my data inputted. just like we were using the software, right? I'm going to check my form. These are always 0 because this is where your optimal solution is going to arrive or going to be placed when Excel solves it. I'm going to check my formula here and check my formula here and here. And this one, you know, we don't have a third constraint. I'll just remove it. This formula, before I click on it, should be taking whatever this is going to end up being and whatever this optimal solution is going to be and multiply them by the corresponding numbers in the objective function, 2 times optimal solution of A, 3 times optimal solution of B, which will appear here. So this should be cell locations of this, 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 and this. Down here is taking the optimal solution and multiplying it times its corresponding numbers that are with the variables in the left-hand side of each constraint. So right here, E9, E13, F9, F13, just like it should. And if this had another variable, I'd be adding to that G9, G13. If I had another variable, H9, H13 be added to that. So I just expand that formula. Down here, I'm going to check to make sure. Again, this constraint's numbers are up here, E7, E13, F7, F13. And if there was another variable in that constraint, G7, G13, maybe. And if there isn't a variable in that constraint, remember the one on the PowerPoint only had A is less than 6, then this would have a 0 here for B, and it would automatically, you don't even need to change the formula because 0 times anything would just eliminate it anyways, like not having B in the constraint. And this formula, same thing, optimal solution, but it's going to these numbers that are with the constraint, the 5 and 3. So this times 5, this times 3, give me that number there. Here's the deal. You're going to want to add right here, a slack or surplus calculation, which is going to evaluate what this turns out to be compared to what the right-hand side is. So let's see. But we know that this should end up being a 6, and that should be 15 because there should be 0 slack or surplus, right?
Well, an if statement, if we were to put an if statement there and said if that has the less than or equal to.
You don't have to, because I want you to tell me what the slack or surplus is, even if it's 0. I don't even need the if statement, because I want something there no matter what. The if statement is going to decide whether a calculation needs to be done or not.
Right.
I want it, even if it doesn't need to be done.
Okay.
So I just want you to take, in this case it'd be J, what do we got here? This is J19 minus, and what row is that one in? E19? There we go. Now an if statement could determine whether it's slack or surplus.
Right.
But I got to think about this. Here we go. I like this. We're running with it. If, here we go. Here's our if statement. If, right here. This is the only place on this whole thing I could refer to look to see if it says less than, equal, or greater than equal, right? So if cell, what is that? F19. If cell F19 equals less than equal quotation. How's that look?
Mm-hmm.
Then, what do I want it to do if it is a less than equal? I want it to put the word what?
Slack.
Slack. Well, I gotta use quotation. So I hope this works. And if it's not true, then I want it to put the word, we can assume it must be surplus, right? So if it's true, and it is a less than equal, we want the word slack there. If it's not true, we want the word surplus. Here we go.
Just a quotation.
Oh, thank you. Fixed it. But we haven't calculated yet. I'm gonna copy and paste. Do I need cell location? Okay. Did it change it to F20? Yes, it did. We're good. This I gotta copy and paste this. It's gonna calculate. There we go. Ready? How do we solve it?
I think it's wrong though. Because
What's
it
wrong?
says surplus, it should say slack.
Oh, what's Boy, that should work, shouldn't it, you guys? It should say slack, shouldn't it? What did I do wrong with the if statement?
I don't think you need a dash there.
Which dash is that?
The one after the after less than, I think you just put less than equal to.
I thought, wouldn't you have to copy that exactly as in there? I tell you, I think I can figure out a way to make this better though. Watch this. If I get rid of this and this, Oh, you know why? Because it's comparing this number and it's zero. It's not, no, it's looking here, isn't it?
Do you have a space in front of that symbol?
Let's take a look. Space in front of,
On F19, if you go to the cell F19,
good call,
are you up to the,
because it's centered. Oh. I see what you're saying. Hang on a minute. There, thank you.
Nice.
Matter of fact, I can go back to the slash equals now, couldn't I?
mhm. But you wouldn't need to, would you?
See what happened there? Because I had spaces in front of it here. It's centered now because I clicked up there and centered. That's what was causing that to assume it was not exactly a less than equal. Let's solve it. Data, solver, does E15 have our objective function formula? Is this a max? Does E13 through F13 have where we want our optimal solution? Does the constraint, I want to enter these, so I'm going to do that. Ready? I'm going to do the constraints. I'm going to add a constraint. It's wanting to know cell reference, which is going to be E19. It's a less than equal. And the right hand side will be J19. Does that sound right? Okay, now I'm going to add one more. The left-hand side would be right there in E20, less than equal. The right-hand side would be at J20. Let's do OK. There's both constraints. There's where we want the optimal solution. This is a max problem. There's the objective function cell being calculated. I make sure the box is checked that, there it is, unconstrained variables are non-negative. Our decision variables are non-negative. We always have to have that box checked. We got to make sure this is doing simplex LP, not the G. When you first start this, it's going to be GRG nonlinear. You want to switch that to simplex. It's solved. We should get 1.72 and 2.14, except we rounded one wrong. And sure enough, 1.71 and 2.14. And look at that, it's a 6. Look at that, it's a 15. And we just got to fix this because of that spacing, and it works perfect. And I'm not saving this. All I did was take the one that was saved, that's posted for you guys, and just make some changes to it to tailor it to this problem. And it will be, it's easy to use. I just hope you practice it a few times. Because if you don't practice it, you'll go, okay, where do you go? Like solver's a hard thing to remember. You got to go to solver, which is under the data tab. I think I gave you a page number though. If you make sure and remember page 89, it shows you step by step to how to do this. Go to the data tab, find solver, what's being entered in each one of those. And if this were on a quiz, you may have a picture of an Excel spreadsheet like this, but this is possibly open. And the question may be, what are you putting in that blank spot that says set objective? And you're looking at this. You're going to put E15 is going to be your answer for that question if this is on a quiz. We get it? All right. I'll fix that on my own time because I'm not going to save it anyway. Any questions? Oh, wait, we got an in-class.